with his talk about spatial data analysis with SpatialDependence.jl. Round of applause for our speaker.
Okay, so thank you all for being here. So I'm going to present this package, which is one of my first packages I developed for Julia. This is basically a package for what is called exploratory spatial data analysis, okay, which is basically the standard exploratory data analysis, but with a spatial dimension. So it allows to create what is called a spatial weights matrix. I will go on this soon. And test for what is called the global and local spatial autocorrelations, and to make choropleth maps. So let's better see this with an example. Let's imagine we have some data about unemployment rate in US counties. We want to ask the question, is unemployment in one county related to unemployment in neighboring counties? Yes or not? And if yes, to what extension? Okay, so to perform a spatial analysis, we have to do some steps. Of course, in Julia, the first step is to load the package with the using command. And then we need to import some geographic data. And then we can start making some map, create a spatial weight matrix that collects the relationship between our spatial observations, and then compute some statistics for a spatial autocorrelation. So for importing data, here we take advantage of the GeoInterface.jl, this interface for working with geographic information, geographic data. And in fact, thanks to this GeoInterface, we can read data from many Julia packages like shapefile.jl or geodataframes.jl. This is very easily. We just read the shapefile or the geodata frame, and with a single command from geodata frames, we can read our geographic data. And once we read this data, we are ready to use the spatial dependence package. So the first thing we can do is to make choropleth map, which is this map where we have, for example, here, all the counties in the US with their employment rates, and we can set colors based on equal intervals or quantiles of our data or natural breaks to have pretty maps. We can also what is called some statistical maps that to classify these observations based on the standard deviation or percentiles. Okay, we can also have other kinds of maps, have unique values. And to make this map is very easy because we take advantage of the Julia interconnection between packages. So using the plot function from the plot package, we can use, say, plot. We pass the data object, the geographic data object we have read before, then the variable we want to plot, and the kind of map. It can be a quantile map or a natural break maps, for instance. Then we also have functions to compute a spatial weight matrix, which is basically a matrix that contains the information of how our spatial units are related. Let's imagine we are this red box here, and let's ask which are the neighbors of this US county. So the neighbors are the dark blue boxes, the dark blue polygons. And we can create this matrix very easily with just one single command called pollinate. And then we create an internal object that is used before for the autocorrelation statistics. We can create a spatial weight matrix from polygons like US counties or European countries or European regions or whatever. Or for instance, if we have that our observations are firms or households, we can create this connection matrix based on a distance threshold or a k-nearest neighbors algorithm. Then we can compute a spatial autocorrelation statistics, which basically to answer the question, is variable x correlated with the value of its neighbors? The most famous spatial autocorrelation statistics is called the Moran index. We can compute this with a single command. Just set which variable we want to compute, and the spatial weight matrix we have calculated before. And then we get the results, and we can print the results in Julia very easily. We basically get a correlation coefficient that goes from -1 to 1. Here we get a strong. We also have statistics for significance. And thanks to Julia, because this statistics is made with random permutations of the data, thanks to Julia, this also works in multi-threading and is very, very fast. We can also make plots, what is called like a spatial Moran scatter plot that relates one variable, which the the value in its neighbors, and then we can make a map very easy in Julia. But also we can look at what is called local spatial autocorrelation, is to test or to check if there are spatial clusters in our data. Here we have an example for the unemployment rate in US counties. And for instance, we can see that these dark blue colors, the dark blue counties are counties with very low unemployment rate, whereas the dark red are counties with very high unemployment rate. So we can see that there are some spatial patterns and spatial clusters in our data. And now a bit to finish about my experience developing this package. I want to say that this was a very fun and rewarding experience for me. I learned a lot of Julia and how Julia works internally, like for example, how to do multiple dispatch, how to optimize code, how to use multi-threading, how to work with GeoInterface and other interface in Julia. Also, just want to say that this package is inspired a lot with what is already available in R, in the SpDep package, and in Python PySal and in the Yoda software. So I try to bring everything that other researchers are using in Python in R. This is used a lot by economists, social scientists, and political science. So I try to bring everything to Julia. Also, while maintaining the Julia own style and language. And this is still a work in progress, and more function is yet to come. And that's all. Thank you very much.
Any questions?
Yeah.
Thank you for your presentation. Can you tell us what's the main advantages of using Julia while we are interested in spatial analysis?
The main advantage is when we are working with very big data sets. For example, in US counties, we have a lot of counties. Also, for instance, if you work with European regions or European municipalities, when you want to compute this neighborhood matrix, the W matrix, or when you compute the local spatial autocorrelation, to test statistical significance, you need to do this permutation test with a lot of replications. This in other language was very, very slow, but in Julia it's quite fast, and also thanks to multi-threading is even faster. So the main advantage is quite fast. And also the syntax, I try to make the syntax as easy as possible and homogeneous across all functions.
Yeah, just a short question. Thanks a lot for the presentation. So you showed like in the constructor of the spatial matrix, there are a few hyperparameters, right? Like that you enforce to build your spatial matrix, right? So I just, if I understood it correctly, so are there ways to infer or like to estimate these parameters of the spatial matrix you are building?
Yeah, well, in the spatial contributory matrix, basically, if you have polygons, it's basically what is called like binary contiguity. If you share like a common border, then you are neighbor. That's the algorithm is quite easy in this sense. When you have points like firms or households, you can say, okay, you are my neighbor if you are like 5 kilometers away from me.
Right. Okay, so you enforce that, right? So you basically say, okay, this is good.
Yeah, you have to decide which criteria to use.
All right. Yeah. Thanks.
Oh, I think there's.
No problem.
Thanks for the presentation. Just a previous question triggered a question for me. How do you handle geographic units versus projected coordinate systems? So do you account for that? Let's say latitude and longitude versus things in meters?
Well, for these kinds of analysis, this is not very relevant, because when you build the contiguity matrix, the relation matrix, you can say it will be 5 kilometers or it will be 10 kilometers or whatever. And for the distance, we use the distance package. So in theory, we use the units embedded in the geographic system.
Okay, thanks.
Yeah.
It was a really great talk. I'm so pleasant with these maps when we do clustering on the map. It's really nice. So I hope you enjoyed this talk as well. So just a round of applause for our speaker.
Thank you very much.